in the beginning of chapter 11, we discussed sequences, right? So a sequence of numbers, usually with some sort of formula. For example, this one, right? Famous geometric sequence where the nth term here is 1 over 2 to the actually, I'm going to say n minus 1 because we started with 1. Now, in series, in discussing series, we actually take all the numbers in the sequence and add them up, right? So what do I have? 1 plus 1/2. And I will spare you all the jokes about an infinite number of mathematicians walking into a bar, and just start with thinking about what something like this means, right? Now, the problem is you're adding up an infinite number of positive numbers. So you might think, well, that seems like you would always be going off to infinity because you're adding up an infinite number of numbers. Although in this class, we already have seen times when we took some integral, some infinite thing, area under a curve, and it turned out to be finite. So you can imagine that sometimes this works and sometimes it doesn't. Sometimes we can add up the numbers and get a finite number. Other times we can end up adding all those numbers and it goes off to infinity, right? So we are going to be sort of studying that a little bit now for the next couple of weeks, okay? Because there's a lot to talk about in series. But I'd like to talk, first of all, just sort of to help you get a feeling for what's really going on here. I do have a Geogebra worksheet that I thought was kind of nice. We can take a look at. Hopefully I can get this so that you can see the whole thing. Here's my theory. A lot of times people use K rather than N. I like to use N, and our book uses N. So, but if you see K, then it's not a big deal. So the first thing is, in terms of summation notation, when I write this thing down, I can write it down with summation notation. So here's your summation here. You can see though that we begin here. Whoops, I don't want to do that. I want to do this. We begin here with just k equals 1, which means it's one term. So the first term in the sequence is 1. So my first term, if I add up just one term, I'm going to get 1, right? So now if I start adding up the number of terms, well, let's start here. So what this applet does on the top, this is the sequence. This is just the individual terms, 1, 1/2, 1/4, 1/8, etc. So they're giving you all the numbers here. And then underneath is actually, I could have done it that way, right? Underneath is actually the series. So here, this is of course not to infinity yet. This is just the first 13 terms, but you can see what's happening with these because these guys get so small. Even after 13 terms, you can see the way it's, the first one is green, the second one is red, and then it goes green, red, green, red, as they're summing it up. So the sum, and what this is called a partial sum, right? It's not the sum as n goes to infinity. This is the sum as n goes to from 1 to 13. So it's like the first 13 terms, right? So as that number of terms that I'm adding there increases, we can see this example that this sum does look like it's not going to go too far. So if I make it go bigger now, okay, now we're at 2. Now, at that point, after this n equals 24, n equals 25, it's actually going to continue to 2 because this thing doesn't have, but it's like not, it's only rounding up to 2, right? It's is really like 1.999999999, right? Because each one of these here, if I look at 1 over 2 to the 23rd, that's such a small number. It's not 0, but it's extraordinarily small. Okay, so because this is going up so fast, because this is going down so fast, this can't go up any further. And we will prove this, that in the limit, this will do that. And we have a formula for these special kind of geometric series. Now, there are lots of series that are not geometric series. Let's look at some other ones. And I'm going to hope that I can get this to work without it going all wacky on me. Yeah, well, I probably don't want that. How about just 1 over k plus 1? So I can start with, no, see, that's the problem I have with this thing sometimes. You press the wrong button. There we go. In fact, let's just make it 1 over k. 1 over k, this is our harmonic series, right? So this, let me write this on the board here. We had n equals 1 to infinity of 1 over 2 to the n minus 1. My next example, instead of being 1/4, 1/8, it's going to be 1/3, 1/4, 1/5, a plus. So this is 1 over 10. Let me, oh, I forgot to make it small. So hold up. So these are sort of two examples we're going to look at. This is an example of a geometric series. This is called the harmonic series. But what we're really looking at in the applet, of course, is not an infinite number of terms, but some sort of finite number of terms. So this was the next example. What we're looking at is what's called partial sums. So S sub n, yeah, I think your book uses a big N, is the sum from little n equals 1 to big N of whatever your series terms is. So in our case, it would be the sum from little n to big N of 1 over n. What does that mean? It means, okay, if I just look at this, S1 is just the first term. So it's 1. S2 is the sum from n equals 1 to 2 of an, so it's 1 plus 1/2. S3 is just going to be 1 plus 1/2 plus 1/3. S4, etc. So these are those. Each of these sums is a very normal finite number, right? So if I pick a specific n, I just have a regular sum. The trick of the problem is that if I want to take n to infinity, what I have to do is I have to look at these numbers, the numbers that are the partial sums, and look at the limit of that, right? So just kind of keeping that in mind, let's look more at just some examples to get a feel for it. And then in another video, I'm going to go into more detail about what I just said about limits of sums, limits of partial sums. So here's our example of the harmonic series. Like you can see, so what it's doing here is it's graphing those partial sums, right? So for, let's see if I can make it smaller. For this guy, up to 5, you can see they're going here. It does keep going higher and higher, but it's not going like super, let's make it go. I don't know if I can, oh, I can do this. The problem is I don't think, oh, it does. does. It moves. You can move this stuff around. How cool is that? So now I can actually see it a little bit better. This one doesn't seem to want to move. Anyhow, when I'm playing with this, I can kind of get some picture. It's not clear here, right? It looks like it's going, it keeps going up, but it is going up, it's slowing down with it's going up. So when I'm looking at this picture, it's not as clear for the previous example, definitely it got to 2 real fast, or very close to 2 real fast. Here, maybe it goes to 5, maybe it doesn't go to anything, we don't know. So this is going to be, oh, sorry about that. This is going to be an open question for us that we will be thinking about throughout, and we'll get the answer. We'll prove that this actually diverges. It doesn't go to any number. But that's not easy necessarily to see. So let's look at some different ones. You know, just for kicks, we can look at anything we want. K plus 1 divided by K plus 2. Okay. Let's see if it does that. Whoop. It doesn't like me. Yeah. All right, let's go back so we can see it a little better. Okay. So now if I look at this sequence, I kind of know that what this sequence is doing, right? K plus 1 over K plus 2, we've seen it. If I look at just the sequence of points, it's getting pretty close to 1. Okay. And we can see that with the, just by taking the limit here. We know the limit's going to be 1. So, well, here, by the time, whoop, anyhow, I'm pretty close by 20. By 20, I'm pretty close to 1. So that's what the sequence is doing. But what does that tell me for the series is the question that I had. Because look what ends up happening. I don't know what it's doing there. What ends up happening is that at this point, I'm adding, each time I'm adding something that's very close to 1. So basically, this is going to go up and up and up and up to infinity. So even though by 20 terms, okay, it's only to whatever, not quite to 20, but it will still, at this point, each time I'm adding another term, I'm going to be adding another 1. So if I look at what these sums are doing, they're just going to kind of keep going up this way. Okay, so this is an example of like a classic divergent sequence where this is just not ever going to approach a number because each time I'm just adding another 1. Okay, and so what did we have? Okay, and here's like another example. Here's a good, let's actually, sometimes it's better to, okay. So we had 1 over K. Another example is 1 over K squared. Okay, again, we start from 1. All right, so sort of similar to the 2 to the n, but not quite as fast. But you see what happens, this guy, we know also goes down to, it goes down to 0, and it goes down pretty fast. And I don't know why this is now so small. Okay, maybe I can make this a little bit larger. Sorry, guys, I lost this thing. It went away. Wow. All right, let's put this here. Let's make this bigger. All right, so anyhow, this is a sort of an interesting point, and we will actually be looking at this later on. You can see just sort of heuristically, this one also does look like it's converging to something. Because here by 17 or 18, I'm still adding something, but I'm not adding something very big. I mean, it kind of looks like it goes to some number. I don't know exactly what number it is, but you see it's still going up. So I'm not entirely sure where, in fact, I don't know. I don't know what the limit of this is, I forget. But it's not something that's easy to figure out analytically. Like this limit is one that we just calculate by adding stuff up. Okay, but what we can do and what we'll learn how to do is, regardless of if we do or do not know what number it adds up to, we will learn how to tell whether it is going to be convergent or divergent. So in this first section, 11.2, we're going to be able to look at some sequences where we can figure out what it converges to. But then later on in the chapter, okay, now my thing is completely, I wanted to show you guys another one, but anyway, we'll make it redo. And later on in the chapter, we will just be learning how to check if the sequence is convergent or divergent without necessarily figuring out what the limit is, without necessarily figuring out what it converges to. All right, well, I'm just gonna stop this now then because it's not working. Okay, so in the next video, we're going to get a little bit more mathematical, a little bit more serious about what this actually means. But keep those pictures in your mind and feel free to go and play on that worksheet and see what different things happen.